In our previous set of mini lectures, we talked about waves and simple harmonic motion, and we also started to think about light. Now we're going to start really thinking about how light is a wave and how those waves interact or interfere with each other to produce constructive and destructive interference. Wave optics is the study of how we can use the interference of light and treating light as a wave to our advantage. So here I've got a couple of examples of wave optics. Wave optics turns out to be important in astronomy. It turns out to be important in many aspects of physical science. It's also important to understand how our eyeballs work, among other things. Down here is an example of a laser beam that's passing through a grid of vertical slits to produce an interference pattern, which is characteristic of waves. So we have light interfering constructively to create these bright points, and waves interacting destructively to create these dark points in between the bright points. And so we're going to play around a little bit with this in lab for the next few weeks as well. Now, you might have heard of something called the wave-particle duality. Okay, that's this bizarre thing with light where sometimes it's to our advantage to think about light as a wave. Sometimes it's to our advantage to think about light as a particle. And that light particle we call a photon. Photons are individual packets of light. The thing about light is that it is both a particle and it is a wave. But for now, we're going to be thinking about light as a wave. Later on in the semester, we'll also think about light as a photon, light as an individual packet of light. Actually, there are three models of light that we can use to describe how it behaves. Okay, so each model successfully explains the behavior of light within a certain domain. Right now, we're thinking about the wave model of light. Light behaves like a wave, like sound or water, like we've been already talking about. This is useful for understanding interference, how light interferes constructively and destructively, which is going to be the topic for our next few mini lectures, and that's the topic of wave optics. We also have the ray model of light, where we can think about that wave, but that light travels in a straight line, and that traveling of light in a straight line, we can call that a light ray. We can draw a straight line to represent the direction in which that light is traveling, and this is useful for studying lenses and mirrors, which is geometric optics, which we will get to as well before we take our first exam. And then we've got this photon model. That's our individual packet of light. Light consists of these discrete quantized particles called photons, which are useful for studying quantum effects. Quantum effects are things that happen on very small scales, like on the scale of particles and subatomic particles. That's something that we are going to hit on in the very last week of the semester. We'll talk about what we call modern physics. Then to recap, light is part of what we call the electromagnetic spectrum. We've got oscillating electric and magnetic fields. That is the wave model of light that we're talking about now. All parts of the electromagnetic spectrum, no matter what their wavelengths, no matter what their frequency, travel in a vacuum at the speed of light. Okay, so the speed of light in a vacuum, we represent a lowercase c, 3 × 10⁸ meters per second. And visible light, that's the light that we can see with our eyes, has wavelengths that range from 400 nanometers, this is like the violet end of the rainbow, and then up to 700 nanometers. 700 nanometers is the red color in the rainbow. So that's our visible spectrum that human eyes have been created to see, okay? So because our wavelengths are really short, especially in the visible, okay, nanometers, 1 nanometer is 10⁻⁹ meter, the frequency of visible lights are very high. So remember we said that the speed of of a wave is equal to its frequency times its wavelength. So if we solve that equation for frequency, frequency is equal to the speed of that wave divided by its wavelength. So if we're thinking about light traveling in a vacuum, our 600 nanometer wavelength of light, which is a red wavelength of light, let's say it's in a vacuum, so its speed is 3 times 10 to the 8 meters per second. We're dividing it by its wavelength, 600 times 10 to the minus 9 meters. 1 nanometer is 10 to the minus 9 meters. So that gives us a frequency of 5 times 10 to the 14 hertz. Now, this tells us that for every second, we have 5 times 10 to the 14 complete cycles of this wave that pass any given point. That's what this frequency means. Now here again is our electromagnetic spectrum, because I want you to get into your brain where the visible wavelengths of light sit on the electromagnetic spectrum. So this is a slide that I show my astronomy students when we talk about light. It also works here. So we've got, in this graph, we have on the left, very short wavelength, very high frequency waves. Okay, that's our gamma rays and our X-rays. These are also the ones that have the greatest amount of energy. And then over here on the right, we have our long wavelength, shorter frequency waves. Those are our radio waves and microwaves. Okay, in a vacuum, all these waves travel at the same speed, 3 times 10 to the 8 meters per second. Now, the visible part of the electromagnetic spectrum inside here, those are the colors of our rainbow. So if you remember, maybe when you were younger, you learned about the colors of the rainbow. I learned a mnemonic. Think about the name Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Those are the colors of the rainbow, okay? So the red end of our visible spectrum, that has a wavelength near 700 nanometers, higher wavelength, okay? Larger wavelength, let's say. And then down on the violet end, blue, indigo, violet, yeah, of the electromagnetic spectrum, we have violet, purple colors of the visible spectrum, and those have shorter wavelengths near 400 nanometers, okay? And sort of the greeny colors are in between 500 and 600 nanometers. Remembering that light travels at 3 times 10 to the 8 meters per second in a vacuum. But what happens when light enters into a medium? Light waves slow down as they pass through transparent materials like water, glass, or air, okay? This slowing down of the wave is due to interactions between the electromagnetic field of the wave and the electrons in the material through which it's moving. That sort of slows down that wave, okay? So the speed of light in a material is characterized by the material's index of refraction, which we represent as lowercase n, okay? So the index of refraction is really a ratio. The index of refraction is defined as the ratio of the speed of light in a vacuum, 3 times 10 to the 8 meters per second, divided by the speed of light in a material. So that speed of light in the material, you know, that's something that's determined experimentally in order to get you the index of refraction of a material. So over here is a little chart. The index of refraction of a vacuum is exactly 1, okay? There's no particles there, all particles have been pumped out, okay? The index of refraction for air is very close to 1, so we'll still use 1 for it in this class, okay? The index of refraction of water is 1.33, so that means that waves of light slow down when they enter water. The index of refraction of glass is even higher, 1.5. The index of refraction of a diamond is 2.42, much higher. So that means that light slows down a lot more inside a diamond. You know, that's why our diamonds sparkle, okay? You've got a lot of the wavelengths of light bouncing around inside that diamond, and they're slowing down a little bit. They've been slowed down inside that medium. And so it makes them really great sparkly objects. If you cut the faces of those diamonds just right to get just the right reflections happening inside the diamond, and refractions. We'll talk about what it means to reflect and to refract in a minute. Now, n is always greater than 1. Your index of refraction will always be greater than 1. It's defined as 1 in the vacuum. Any other medium, the index of refraction is going to be larger. When a wave enters into a new medium, its speed can change, or will change. Okay, its wavelength will change, but its frequency never changes. So the frequency of a wave never changes whether we're in a vacuum or in another material. Okay, that same wave frequency doesn't change. The wavelength of light inside the new material is going to be equal to the speed of the wave in the material divided by the frequency of the material. That's taking our speed of a wave is equal to the wavelength times frequency and rearranging it. Okay, and in the previous slide, we saw that the index of refraction is equal to the speed of light in a vacuum over the speed of light in the medium. So I can replace the speed of light in the medium here with the speed of light in a vacuum over n. So that's what's happening here. Then we remember that the frequency of the light doesn't change no matter what medium we encounter. So we can replace the frequency of the material here with the frequency inside the vacuum. And then from our equation for the speed of a wave equals frequency times wavelength, we can rearrange that and show that the speed of light in the vacuum over the frequency of light in a vacuum is equal to its wavelength in the vacuum. Okay, so now we have a new expression where we can show that the wavelength of a light in material equals the wavelength of the light in the vacuum divided by the index of refraction. So we have a new ratio that relates the wavelength of the light inside and outside the medium with the index of refraction. And that's also listed in your equation sheet, but it's listed as the index of refraction equals the wavelength of light in the vacuum divided by the wavelength of light in the material. And that's the same thing as rearranging this equation right here. So because of that, if we look at this equation here, the wavelength of light in the transparent material is always going to be shorter than the wavelength of light in a vacuum. Why? Well, the index of refraction is always going to be greater than 1 for any material. So if you take that wavelength of light and you divide it by a number bigger than 1, you're always going to end up with a smaller number. So your wavelength of light inside the material will always be shorter than it is outside the material. Even though the wavelength of light changes in the medium, the color that we perceive with our eyes does not, because the color of light that we perceive with our eyes is dependent on frequency. And since the frequency of light doesn't change, we do not see a different color, even though the wavelength of that wave might change when it enters into a new medium. Now we're going to apply these ideas that we just learned to solve a problem that's similar in some ways to a workbook problem, and also is related to the engagement check question that goes along with this mini lecture. For this problem, we are going to have orange light with a wavelength of 600 nanometers. And this light is incident, that means it's striking on a 1 millimeter thick piece of glass. So I'm going to call that T. T is equal to 1 millimeter. Okay? The index of refraction of our glass, which we represent as N, is equal to 1.5. Okay, so we've got 3 different questions we want to answer for this problem. Okay, maybe I can just draw a little diagram of what we've got going on. Here's my 1 millimeter thick piece of glass. Here I have light with a wavelength of 600 nanometers. It's coming in and it's striking my glass. It's going to travel through the glass. Okay, so the first question we're going to answer
A, is what is the speed of light inside the glass? To solve this problem, we're going to use the definition of the index of refraction. The definition of the index of refraction, N, is equal to the speed of light in a vacuum divided by V, which is the speed of light inside our material. So we got to solve this equation for V. We multiply both sides by V. It cancels out the V on this side. So V times N is equal to C. We're solving for V. We divide both sides by N. So V is equal to the speed of light divided by the index of refraction. So this is just going to be 3 times 10 to the 8 meters per second divided by our 1.5 index of refraction in the glass. And so then that tells us that the speed of light inside the glass is 2 times 10 to the 8 meters per second. Okay? So that's part A. Part B, what is the wavelength of the light inside the glass? So lambda, I'll call it lambda sub n for the wavelength of light inside the material with an index of refraction that doesn't equal to 1. So what is this? It's not going to be this 600 nanometers, because that's the wavelength of light that's traveling through the air before it enters into the glass. So in order to find this new wavelength of light inside the glass, we're going to use the following equation. N is equal to the wavelength of light traveling through the vacuum, or air, divided by the wavelength of light inside the material, which I'll represent with the sub n. So we solve this equation for lambda sub n, and just like we did over here in a similar way. So lambda sub n is equal to the wavelength of light in the vacuum before it enters the material divided by the index of refraction. Okay, and so then that's going to equal to 600 nanometers. That's the wavelength of our incident light divided by our index of refraction, 1.5. So that tells us that the wavelength of light inside the glass is 400 nanometers. Okay, so the wavelength of light inside a material always changes from the wavelength of light that's outside the material in the vacuum or in air or some other medium. This is going to be like one of your workbook problems. And then C, how many wavelengths of light are inside the glass? So how many of these wavelengths of light are inside the glass? Number lambda n inside glass. So in order to do that, we first had to figure out what was the wavelength of light inside the glass. Now we can use that number in order to figure out how many of these full wavelengths of light are crammed inside our piece of glass that has a width of 1 millimeter. So in order to solve that, we're just going to divide the thickness of our glass, which we'll say thickness divided by the wavelength, okay? So that's going to be 1 millimeter divided by the wavelength of light inside the glass, which was 400 nanometers. Well, let's see. In order to get this number, we have to have the unit on the top here be the same as the unit on the bottom here. Okay, so we have to get these both into the same unit. How are we going to do that? Well, one thing we can do is we can convert millimeters over to meters and nanometers over to meters. Okay, so let's see. I'm just going to do this right here. 1 millimeter is 10 to the minus 3 meters. 1 nanometer is 10 to the minus 9 meters. So I can write it like this. So I have 10 to the minus 3 meters divided by 400 times 10 to the minus 9 meters. And then that tells me that I can cram in 2.5 times 10 to the 3 wavelengths of light inside my glass, or 2,500 wavelengths of this orange light inside my glass.